Hello AP, we're doing 9.2 today, and I have me and my molecule friends with me to help you understand shapes and angles. 9.2 is a beast. It's probably the heart of chapter 9. One, because it's long, but two, there's a lot of things that you need to understand about angles and different types of shapes. Okay, so I'm going to be moving back and forth and trying to move the camera around too, and then bring these obviously closer to you so that way you can see what it physically looks like. Okay, so let's get into this. We learned in chapter 8, we examined how single covalent bonds is formed between two atoms when a pair of electrons occupy that same space as the other atoms. And we have what's called bonding and non-bonding. So in a bonding pair of electrons, it defines a region in which the electrons are most likely to be found. So when you are taking that one element and bonding it into the other element, we're talking about these electrons right there. Those are our bonding. Now, are they being shared equally or not? That's a whole nother story. So in this bonding pair, it's where those electrons are most likely to be found. And we call this region a specific name called electron domain. So this right here, this region where electrons are found, this is its electron domain. It's going to be very important that you don't confuse a couple new terms. So we got to make sure that we take this a little bit slow. Non-bonding, aka those lone pairs, are the electrons defined as electron domains that are located only on one atom. So if you do have that particular atom that it's bonded to, all of these lone pairs surrounding that one atom are only assigned to that one atom. They're not being shared unequally. They're not being shared equally. They are just the bonding electrons only assigned to that one atom. So for example, Mr. Ammonia. And we need to make sure we are practicing names too. So ammonia has four electron domains. So you need to think of electron domains as regions of electrons. Okay? And we're going to make sure we get that in there. Regions of electrons. But we're talking about all regions of electrons. So in those regions of electrons, it could be bonding and non-bonding sites. So if I look at ammonia, I have this bonding, and I have those bonding electrons, and I have those bonding electrons. But I also have lone pairs surrounding that nitrogen too. So because I have 3 bonding and 1 non-bonding, that equals 4 electron domains. So a domain, think of it as a site, a region of where electrons are located. Okay, so as you see right there. So we're always focused on the central atom. So in the Vsepr models, the central atom, as I always like to call the star of the show, he is not only going to predict the shape that that molecule will have, but it will also dictate the angle. Okay, so we need to make sure we are focused primarily on the central atom to determine the shape and angle of molecules. Fortunately, we have many names that we have to learn. Some of them you heard of before. Some of you probably never heard of some of these names, and it's okay. That's what we're going to learn in this chapter. So for each multiple bond, it also constitutes as a single electron domain. So notice right here, if I'm only focused on this central atom, okay, only on oxygen, well, I have these bonding electrons, and I also have a double bond, but that double bond still counts as one region. And this one also counts as a region of electrons. Now, I may have 4 electrons sitting in there, but it only counts as a region of electrons. And then I have a set of lone pairs on that oxygen. So I would have 2 bonding regions and 1 non-bonding region. So my total amount of electron domains is I have 3 electron domains. Now the point of this, ladies and gentlemen, if I compare it to ammonia, because right here, this is Mr. Ozone, O3, there is ozone. make sure you are remembering these names. If it has 3 domains versus 4, they're going to have completely different shape angles. They're going to have different shape names. And polar and nonpolar is going to make a big difference with those lone pairs on that central atom too. So we have to look at everything around that central atom. So please do not think, okay, FYI, double or triple bonds, they only count for one region of electrons. Okay, so just because there's 4 or 6 electrons being shared, it still counts as an electron region. So in general, each non-bonding pair, single bond, multiple bonds, they count as a single electron domain. See, I even put it right there, around the central atom and the molecule. So every electron domain around the central atom matters. Lone pairs, oops, I didn't mean to do that one. Lone pairs and bonds, they all matter. So I'm going to put bonds and lone pairs. Okay, they all matter. The Vsepr model, which stands for valence shell electron pair repulsion. And I know you saw that term in 9.1. So the Vsepr, as we call it, the Vsepr model is based on the idea that electron domains are negatively charged and therefore repel one another. Because you got to remember, ladies and gentlemen, you're talking about electrons versus other electrons, and you know like charges repel each other. So electron domains try to stay out of one another's way. So you see how you have lone pairs on ozone on the top, and then a single bond and a double bond. They try to stay away from each other. So what's going to happen is this is what we call a two-dimensional shape, this ozone that you see right there. But this is truly what ozone looks like. So what happens is it's that key sentence right there that the electron domains, they try to stay out of each other's way. And so then what happens is you will get the lone pairs, and they start to basically take all this space, because right here there's a lone pair sitting there. Oh, I'm sorry, this is ozone. I was thinking water. This is ozone right here. There are two electrons sitting right there, a pair. So because the lone pairs, they tend to take up all the space of the molecule, and what they're going to do is, it looked like it used to be linear, like this, and now it truly looks like this, because the lone pairs bent these bonds down away from the lone pairs. So in this arrangement, what it tries to do is, given the number of electron domains, the best arrangement is the one that minimizes repulsions. Okay, so they want to have as little as repulsions with electron-electron repulsions as possible. Okay, so they will tend to bend each other down and look like this, where it used to look on paper like a linear straight line type of structure, but it actually has this structure, which its true name is called bent. So it will take a bent shape. So ozone has a bent shape. And I'm going to put right here, not linear. So there is a big table coming our way as soon as I get through this part right here, and you're going to see the table with all the names on it, and we're going to go one by one, and I'm physically going to show you what the molecules look like. And I even have a cool simulation to help you with this too. There are two types of geometries. You have what's called electron domain, which we just mentioned what electron domain is. But then you also have molecular geometry. So what's the difference between the two? The arrangement of electron domains about the central atom, so we'll call it like AB, whoever it is. But then you see like this little subscript, okay? Hopefully you can see that little subscript. No matter how many atoms that are attached to it, the electron domain is counting bonds and lone pairs on that central atom. It's counting everything around the central. Examine total regions of the electrons around the central atoms, bonds and non-bonding. But the problem is molecular geometry, it only is looking at one part of the central atom. It's the arrangement of only the atoms in the molecules or ions. Any non-bonding pairs are not part of the description. So only focusing on the atoms, aka the bonds, and only the bonds. So what happens is if you have a structure that looks like, let's see, like the ammonia one. The electron domain, there are 4 electron domains. Okay, let me try to make the writing not so thick. There we go. Okay, so because we have 3 bonds and 1 lone pair, that is 4 electron domains. But what about the molecular geometry? For the molecular geometry, it only has 3 domains. And why the difference? So versus molecular versus electron domains is because molecular geometries is only looking at the bonds. It does not look at the lone pairs. Okay, so we're looking at 3 bonding, 1 non-bonding. So right here, non-bonding pairs are not part of the description. So what's going to happen is, because if these two are different, then they have different shape names, which means we have to learn both names. Okay, AP will tell you which one they want. Please list the electron domain shape of this. Please list the molecular geometry shape name. They'll tell you which one. Unfortunately, we got to learn both. Okay, so to determine the shape, here's the rules. First, use the Vsepr model to predict the electron domain shape. So you always look at the total regions first. Always look at the total regions. And then determine how many of these regions are bonding versus non-bonding. If the electron domains in the molecule are all bonds, then the molecular will be the same as the electron domain. And that's when life is good. But as soon as I say something like this is carbon with 4 hydrogens. Okay, and we're going to start looking at colors too. I see 4 electron domains. I see 4 bonds, no lone pairs. So because there's no lone pairs, 4 bonds. So this is what this statement is saying. So something like, if 4 bonds and no lone pairs, then the electron domain name and the molecular domain name, they are the same. And this is what we call a tetrahedral. Tetra means 4. However, as soon as I take a bond off, and now, see that hole right there? That constitutes as lone pairs. As soon as I take that lone pair, put some lone pairs on there, the names are not the same. It still has an electron domain, a tetrahedral, but now that you have those lone pairs at the top, its molecular name will change, and it's something called trigonal pyramidal. Okay, the names are coming. There's our chart. Excuse me. If one or more domains involve non-bonding electrons, then the molecular geometry involves only electron domains due to bonds, even though the non-bonding pairs contribute to the electron domain geometry. What's going to happen is you're sometimes going to see probably more bonds than lone pairs. Or will you see more lone pairs than bonds on the central atom? So what happens is if one or more domain involves non-bonding, then the molecular geometry involves only the electron domains due to those bonds. So it's the example of, does it have 4 bonds only versus 3 bonds plus a lone pair? Because if you add that up, that's still 4 on each side, but the names will be different. So to predict the shape of the molecules or ions using Vsepr, draw the Lewis structure of the molecules or ions, count the number of electron domains around the central atom. So it kind of sounds like the rules above. each non-bonding electron pair in each bond counts as one. So like I said, if you have doubles or triples, that still counts as a region. Okay? Be careful with multiple bonds. They only count as a region. Okay? Determine the electron domain geometry by arranging the electron domains about the central atom so that the repulsions are minimized. We want those repulsions minimized as much as possible. And you'll see two big tables coming, 9.2 and 9.3, that have all the names in them. So determine the molecular geometry, non-bonding and non-bonding around the central atom. Okay? So that's what we need to concentrate on. 9.2 summarizes the possible molecular geometry when an AB molecule has 4 or less. Okay? These geometries are important because they include the shapes that meet the octet. So in this table that I'm going to do first, this is when NAS works. This is when you will definitely see subscripts, whatever that N is. Oops, that little N that's right there. You will see it either be anywhere between 1 to 4. Okay? So, yay, octet works. Okay? We're going to start one by one, and let's go through the table so you see what categories are what. The number of electron domains, so total number of domains. The electron domain geometry, okay, so this is the geometry name. How many bonding regions and how many non-bonding regions. So AKA, how many lone pairs. Now remember, this is all about the central atom. That's all we care about is the central atom. What is the bond angles? And notice with the bond angle, you do have to include the degree sign. So whatever the number is, don't forget the little degree sign. The molecular geometry. Now these two names, molecular geometry and electron domain, these two are very important because sometimes they'll be the same and sometimes they won't. And I even included an example for you also, so that way you can see it, and I'm going to build it for you on the screen also. Now polar and nonpolar, I'm not going to get to this part till about 9.3, 9.4, because now we're going to see is the molecule, is the whole molecule, is it polar or nonpolar? And what you're going to find out is just because a bond, just because an atom has, just because a molecule has polar bonds, doesn't mean the molecule has to be polar. It can be nonpolar in the end. So it's going to be a little trickery going on. So let's start with two regions, okay? Two regions, and the first name is called linear. You will notice that these two names are the same, okay? So two regions, and let me give you a first example, just a normal type of two-atom bond, okay? What happens if you don't have a central atom? So somebody that's like maybe like HF, okay? HF, and usually hydrogens are white, and I'm going to make a little color key. So white, in the pictures you will see are hydrogens. Black ones are carbon, red are oxygens. Usually green are any halogen. So fluorine, chlorine, bromine, any halogen, okay? You will tend to see, thinking of other colors, sometimes blue could be nitrogen or phosphorus because they tend to have 5 holes. Let's see, what else? Purple. I'm going to even put purple on here too, or purple. And let's see. Oops, sorry. And usually these yellow ones tend to be sulfur. I don't usually use the yellow ones too much, okay? But the halogens right here, as you see, only have 1 hole because they only have 1 available electron to bond with. So what if this was like hydrofluoric acid? How do you determine the shape if there's no central atom? Well, you literally look at the bond instead of the central atom. Like somebody like this, I'm only focusing on this carbon right there in the middle. I don't have a central atom. So what you're doing is comparing two atoms with no central atom, and that will always be linear. So basically any two atoms only, and no lone pairs because there is no central atom, like HF or diatomics, okay? They will always have a linear shape, okay, just like this. And when you do the bond angle, you're going from one atom all the way to the other. And the last I checked, for a circle, always think of a circle. If a circle is 360, okay, well, half of a circle to get from one side to the other, and then to get to one side of the other, that's 360. Well, half of 360, there it is, 180. So as you're doing this, you have to start to learn at the bond angles and the names, and that should be very simple for just two atoms. Let me show you one that actually has more than two atoms, like carbon dioxide. And I built carbon dioxide for you because with carbon dioxide, as you see in the picture, carbon, two double bonds on each side, and you can actually make the bonds bend like that too. So carbon's in the middle, two oxygen. But notice with carbon dioxide, it doesn't have any lone pairs. So look at the Lewis structure, because I'm always going to have you draw the Lewis structure first. The Lewis structure right there, there's no lone pairs. So look, two bonds, no lone pairs on the central atom, and that will still have a linear shape. So going from this carbon all the way over to this carbon, that is 180. And if I go down to here, it is still 180, okay? And it's still linear. So only looking at the central atom only, because the tricky part is these oxygens on the outside, as you see in the Lewis structure, they got lone pairs, but that doesn't mean anything for the shape. The shape is always determined by the central atom, okay? Let's crank it up with 3. Now, one thing also I want to mention on here, these purple things, I like to call them the balloons. Please don't draw these. Do not draw these balloon purple shapes on it, because basically those are just either bonds. That's all it's representing. It's just electrons, okay? Sometimes when you get in structures like this, they're trying to show you that there's lone pairs. So basically these AKA balloons are just electrons. Whether they are bonding electrons or lone pairs, it's still electrons. But please don't draw balloons, okay? Please, please, please don't, okay? So now let's see, we have trigonal planar. I was trying to find one, but we'll just use this guy, okay? So trigonal planar, like this, okay, makes a triangle. That's why it's called trigonal, okay? So trigonal, tri, 3, okay? Planar means flat. And I can't make this guy really truly go flat because I'm using the wrong color of the bond, because this is for nitrogen. But usually trigonal planar, if you had 3, and I'm going to put the word right there, planar means flat. So if I actually put this like on a board like this, or paper, or my hand, it should literally be flat on the table. So just like if I move this right here, the camera, if I move it down, it should literally be flat on here, but because I'm using the wrong color, I don't have the right color here, so that's cool. It kind of pops up like a tripod. Okay, so that should be planar, because planar means flat. So always think of it like a piece of paper. Okay, and I'll just keep the angle like that, so that way you guys can see the molecules while I'm using them. What if you had 3 bonding, but 0 non-bonding? So basically no lone pairs. So it would look like this structure. Okay, and greatest example is boron. Boron tends to do trigonal planar. Okay, anybody group 3 will do trigonal planar. Group 3, like boron, aluminum, gallium, they would all tend to have this shape as long as they have no lone pairs on that central atom. So they would have this right here. And what you would see, like I said, trigonal planar, just like that. Okay. However, what if we take a bond off, literally snap a bond off, and there you go. It's not trigonal because now I have 2 bonds, but now I just created some lone pairs at the top. So that's why I like these, ladies and gentlemen. We're going to do a lab with this, and you guys are going to build this in the lab, but you're going to have to do it electronically through a simulation. So I love to do this lab in class because it kind of is like the light that you see, the kind of the aha moment is with these empty holes that helps you know that you have lone pairs. So right here, an example would be like nitrogen dioxide as an ion. I could even tell you ozone. Ozone does this too, okay? As you saw in that picture where you'd have a lone pair, double bond oxygen, and single bond just like that. That is its true shape, okay? And it has what's called a bent shape. So notice these two, because there is no lone pairs, they have the same name for the electron geometry and molecular geometry. But because this one does have a set of lone pairs, these two names are different. Okay, so different shape names. So if you're asked on the test, and if I gave you this molecule, ozone or NO2 -1, if I ask you the electron domain name for this molecule, you tell me trigonoplanar. But if I ask you molecular geometry name, it's called bent. So pay very, very close attention to which one you're being asked. So any of these two examples would have, right here, as you see, it would have a bent shape. And it looks like it's bent too. I mean, it doesn't even look like it's linear. I mean, I can't even stretch it out to even make it look like it's linear. So that right there is a bent shape. So far, NAS would work. Everything would still get your octet rule met. Okay, so now let's change it up to 4 domains. Okay, so this right here. All right, apologies, ladies and gentlemen, doorbell. All right, so now we have right here 4, oops, trying to make sure it's in the screen, 4 bonding regions. Okay, you see 4 bonds, no lone pairs on the central atom. So here's carbon with my 4 hydrogens. And because it's 4, we call it tetrahedral. Tetra means 4. If you have no lone pairs, these two will have the exact same names, okay? Because there's no lone pairs. Bond angles, oh, I apologize. I need to talk about bond angles. Okay, I got a little distracted with the doorbell. Let's go back to this one right here, trigonoplanar. Okay, how do you remember some of these bond angles? Okay, so I got little tricks for them. With the trigonoplanar, okay, think of this right here, the circle. Okay, and remember a circle is 360. And if you take that 360 and divide it by 3, what do you get? You get 120. Okay, but as soon as you put that bond is gone and now you have lone pairs, that bond angle is less than 120. And usually what happens is AP will take the words less than 120, but they're looking usually anywhere between 105 and that 120. So on the AP answer sheet, I don't know why it's all blurry right there. On AP answer sheet, you could actually put the words less than 120, but usually they're looking for any bond angle between 105 and 120. And actually, I don't even want to put 120. I'm going to say 119 because I don't want you to put 120. Okay, and I will accept that too. So less than 120, but only in that range. Okay, if you say like 100 or 90, nope, ain't going to cut it. Okay, it's got to be between 105 and 119. And I'll show you why when we get to this third one down here, why 105. Okay, they would even, no, I'll just stop right there before I get to tetrahedral. So those would be the 2 bond angles that would have 3 regions of electrons. With tetrahedral, it gets a little complex when you get to the angles, because you're looking at the region between this bond going from here to here. And everywhere you go, it has the same bond angles, and it's definitely not 90. 90 degrees would look like something like that if I kind of like bend that bond up right there. But this right here, it's greater than 90 degrees. So what it is, it's 109.5. AP would accept 109.5. They would also accept the bond angle 109. That's totally fine. Either one, that's it. Okay. CH4 would definitely do this type of shape. So this is methane. Right here, this is methane. The more bonds you have, the more possibility of lone pairs. So let's just say I take off a bond and now have a set of lone pairs right there. So now I have 3 bonds, 1 set of lone pairs. My geometry name is going to change from the electron domain to the molecular name. These two are going to now be different because now I've included a set of lone pairs. So right there at the top, lone pairs. And remember, what's the point of the shape name when you have more and more lone pairs? These guys, they're going to take up all this space. As you see in that balloon figure right there, they are now going to say, okay, bonds, this is my space. And they're going to start pushing them down. So basically, you are like bringing, as you see right there, you're kind of like bringing the bonds a little bit closer to each other. When this lone pair on the top, he's taking all the space. So it looks like, if you sit on it, kind of looks like a tripod, like a pyramid. And that's why they call it trigonal for 3, pyramidal. Okay? Make sure you spell these names correctly. I always see the students at the end of the put the D in front of the I. Okay, pyramidal, not pyramidal. Okay, so pyramidal. So now you have a set of lone pairs. So the molecular name is now trigonal pyramidal, but its electron domain still has 4 domains, 1 lone pair and 3 bonds. The name of the game, ladies and gentlemen, it still has to equal that 4. Okay, for this type of domain. So that is ammonia. That is NH3. Now, let's start talking about these wedges and dashes. So what happens is, when you actually have the bond, some of the bonds, as you see, oops, trying to get my camera in there. Some of the bonds, they come at you like they're coming out of the paper. And some of the bonds go straight up and go away from you. So what they do is they do these little dashes and wedges, and basically the solid, we like to call them the dashes. That means that the bond is literally coming at you. Like it's literally coming out of the paper, like it's attacking you kind of thing. Like, ah, there you go, ah. Just kidding. Sorry, I'm having too much fun. And the little dashes, oh my God, I even put the word dash. Sorry. We call those the wedges. I put on the wrong one, sorry. Solid wedges, okay? These are the dashes. So the dashes are going away from you. So like in the back of the paper, okay? So one of these would be coming to the side, as you see right here. One comes at you, and then one goes in the back of the paper. Whether AP draws like solid lines or they draw the dashes and the wedges, it doesn't matter, ladies and gentlemen. It's just a point of view. One's coming at you, one's going behind the paper, and one's going to the side. Okay, so I just want to let you know what these little solids and dashes mean. So the wedges are the filled in bonds, the solid bonds, and then these little dashes right there, they just mean that they're going away from you. What if you keep taking off lone pairs? Okay, so this one right here, I took off a lone pair. Trigonal pyramidal, but now what if I take off another one? And I'm sure it looks like a very familiar shape to you, called like Mr. Water, okay? Whereas if you add these two together, they still equal 4, and they still equal tetrahedral, just like those two added up together still equal 4. However, the geometry, molecular geometry name is going to change to a word called bent. Okay, and with bent, you have a 105, and AP would accept that number, 105. The true angle is 104.5. So I want you to see this cool little trick. So right here, Mr. Methane, right there, every bond angle between each one of them, okay, is 109. As soon as I take one off, notice what happens to the bond angle. All you did was create lone pairs, but you brought these bonds a little bit closer together. And we're talking a little, it's like 2 degrees. So notice the bond angle on here, it's 107. So from here to here to here, it changes by 2 degrees. And if I take another one off and now create, as you see, lone pairs, these bonds got a little bit more closer, because what are the lone pairs doing? They're saying, get away, bonds. This is our space. And they just brought them together even 2 degrees even closer. It always looks like it's more than 2 degrees, but it's not more. So each one of these changes by 2 degrees. Notice right here for bent, for 3 regions, and for 4, same shape name, but this one has 4 regions, this one has 3. The bond angle, about the same, 105, except this one you get a little bit more leeway because you can have anything between 105 to 119. And water is the true one. That is the one that will always remind you that it's bent, okay? So when we draw it on paper, here's the misconceiving part to it. Two-dimensionally, it looks like this. It looks like it's linear, but that's not its true shape. Its true shape is bent. So ladies and gentlemen, when you're drawing on paper, you're going to confuse yourself when you draw it two-dimensionally. So usually we draw it three-dimensionally and draw it like this to show that the lone pairs are kind of like ganging up on the bonds, and it looks like that. That is water's true shape. And I don't want to put those lone pairs on that hydrogen. That is a true shape. AP will always, as you saw on the practice notes and stuff like that, they'll put the symbols in the spot. You just have to figure out where the bonds and lone pairs are. So usually you would see something like this on the AP test where they'll say fill in the structure with electron pairs, bonding, and non-bonding. All right, so then you're going to do this. And then they're going to say, okay, according to your structure, name the shape. Most people will say linear. They obviously didn't learn this chapter because it's not linear. You have to look at it, what it looks like in its true three-dimensional shape. So be very careful. Lewis structures will be very deceiving. Sorry, Jose, my phone went off. All right, apologies, phone going off. Okay. All right, so those are the different structures of when you have molecules that are meeting the octet. So first, look at the central atom, what bonding and non-bonding regions that they have around it. And if you have lone pairs, it is going to change the molecular geometry name. We're now going to start to look at Vsepr when it's expanded octet. In the following notes, ladies and gentlemen, it's literally exactly what I went through. I just want you to read through it, make some notes about when you have structures that still have 4 domains, but you're adding lone pairs, okay? So I'm going to let you go through here to do the notes. I want to show you this simulation. So what I just did right here is exactly what I talked about, okay? When you click on the simulation, this is going to be what our lab is going to be about. So this simulation is going to be very cool to help you with homework questions. It's going to help you with any practice problems you're ever given. And let me click on it so that way you can see it. So always, ladies and gentlemen, control click. And it's the same simulation that we're going to look at for the lab. So right here it's called molecular shapes. And just click on that little play button. And you can do either one. For the lab that we're going to do, we're going to be doing both of them. So with the model right here, okay, so look at that right there. And this is my central atom, the one that's in purple. And if I asked you to tell me what its electron domain is, well, 2 bonds, no lone pairs, because I can add lone pairs if I want, and its name is linear. So just click on the little check marks. And because there's no lone pairs, the molecular geometry name should be the same. Well, let's slap on maybe a set of lone pairs. Look right there. So if I take that lone pair off, look at the 2 names, how they change. So now I have 3 regions. The electron domain is trigonal planar because there's 3 regions, but because there's a lone pair, it changes the molecular name, and now it's called bent. Okay. If you want to show bond angles, there you go. Okay. So for this one, it should have the words less than 120, because if it was exactly 120, like let me take that off, and there you go, there is linear. And if I add another bond on, there's trigonal planar. But as soon as I take this off and just hit the little X button and add lone pairs, it should be less than 120, okay? But I don't think it actually puts the word less, okay? So what if I want to put 4, okay? Well, 4, there's your 109.5, okay? So it's a cool simulation because unfortunately you can't build it in person, but at least you have something to help you with this. And look, if you click on one of the atoms, just hold it down, right click, you can move this guy around so you can see the different points of view. And it's very, very cool simulation, okay? The other one down here, if you click on here where it says real molecules, you can actually see what real molecules look like. Like, look at that. There's Mr. Cool Water. And Cool Water with his 2 bonds and his lone pairs. Okay, so you would see the geometry, electron geometry is tetrahedral, but its true name, molecular name, is bent. And you can even see the angles too. 104.5, remember AP is okay with just 105. And you can do this for any of these. CO2, double bond. We know what CO2 is going to look like, and it's 180. And you can even do some expanded octet ones on here too. Like this one, chlorine, 3 fluorines, you're going to get some expanded octet. Okay, so just drag that around and you can see the difference of it. Okay, so in your lab coming up, you will be using the simulation, and I know it's truly going to help you on how to build this. Okay, so I'm going to keep this kind of handy so then that way we can actually see it built and then see the real show too. So let's go back to here. Draw all possible Lewis structures and predict the molecular geometry. Okay, well, we already know what ozone's going to look like. So ozone, and because it can actually do a resonance structure, we could have this structure, lone pairs. Okay, and we're going to draw our double arrow. And regardless, it is still going to have the shape names because you didn't move any bonds or lone pairs around that changes that central atom. So if you focus on that central atom, it's the same. I have 2 bonding regions plus 1 non-bonding regions, which means I have 3 total electron domain regions. Okay, so 3 total electron domain regions. However, when it comes to electron domain name, it is trigonal planar. But the molecular geometry name is not going to be the same because the molecular geometry, that lone pair. So what's happened? It's going to be a bent shape. And if I ask you bond angle, so bent shape would be 104. Sorry, oops, let me go back, 105. AP would accept 105. They would even accept 104.5 because that's its true shape. What if I had 10 with 3 chlorides on it and a -1 charge? Okay, so with 10, we have to remember that 10 has 4 valence electrons. Okay, and what happens is with these 3 chlorines, you got these empty spots. So I'm going to put these chlorines on. And remember, every chlorine coming in is going to form that bond. So I'm going to get a chlorine there. I'll get a chlorine coming in here. And then I'll get a chlorine coming in here too. So everything looks good. But then what about this lonely unpaired electron? Well, then this is where Mr. Let's gain an electron is going to help it out. So you're going to gain an electron, which means you're going to pair up that lonely electron. So its true shape would look like this. And there is no resonance because in order to have resonance structure, you have to have doubles and triple bonds to move those electrons around, and you don't have doubles and triples. So that is the only possible shape. So focus only on that central atom and count up what you have. Well, I have 3 bonding regions plus 1 non-bonding, so that means it's a total of 4 electron domains. And which ones have 4 electron domains? Well, that's tetrahedral. Unfortunately, because of that lone pair, the molecular name will be different. And the molecular geometry name, as you see in the notes, oops, if we look in the notes right there, 4 regions, but 3 bonds, 1 lone pair, and it's going to be called trigonal pyramidal. So it's going to take us a while to get the hang of the names, but we got to know the names. So trigonal pyramidal. Okay. What would be the angle? Well, remember carbon, always think of methane. Carbon, as you see me building it right here. So carbon with its 4 bonds, 109 degrees. But as soon as I take a bond off, remember it changes by 2 degrees. So the bond angle would be 109, but it changes to 107 because of that set of lone pairs. Okay, so the more lone pairs you have, the more it's going to change the angles. And if I have selenium, selenium has 6 valence electrons. And I don't think it's a no-brainer of what's going to happen. Mr. Chlorine's going to come and bond. So you're going to get your chlorine over here. And let's don't do connect the dots, ladies and gentlemen. I'm going to erase that because that'll irritate me that that's on video. Okay, and so over there. And then we will also, this unpaired electron. And then you get that too. However, is that the true shape? And no, it's not, because what's going to happen is those lone pairs will gang up on it. So you need to think of, that's why they call it the real molecules, the true shape. And those lone pairs, they're going to gang up on those bonds, and you're going to see the lone pairs kind of sit in corners with the chlorines down. I would take any shape, as in any shape picture on the AP test. You can draw it this way, you can draw it this way, but do not call it linear, because it is not linear. You have 4 bonds, so look at that central atom. 4 bonds, I'm sorry, not 4 bonds, I meant 4 regions. 2 bonds, 2 non-bonding regions. So you have a total of 4 electron domain. Well, if you look at right here, 4 electron domain, the domain name is tetrahedral. But from the one we just drew to now I have 2 lone pairs, where this one I only had 1. So it can't be trigonal planar, because trigonal means 3 bonds, and I don't have 3 bonds, I have 2. So now the molecular name, look at it, it looks just like water. It's called bent. And that bent name has an angle of 105. So notice from here to here, every time you took lone pairs off, it changes about, I'm sorry, take a bond off, it changes by about 2 degrees. Okay? So just practicing. We don't have to practice the drawing. We've already done that in chapter 8. We just got to practice the shapes and the names. Okay? What if you have CO3? Well, real quick without the NAS, you would get this. And would you have resonance structure? Absolutely. I have those double bond on an oxygen, and I can move those double bonds anywhere. I can move it to the left or to the right. So you would have an additional 2 other, which you draw the 2 other resonance structures. You would have 2 other resonance structures, but you're still going to have the same shape name. So regardless, ladies and gentlemen, because you have 2 other resonance structures, very key, the shape and angles won't change just because you have resonance. The only thing that changes with resonance is your location of electrons. But you still have, if you look at this structure, how many bonding regions? Well, I have 3 bonding regions. And on that carbon, I don't see any lone pairs. So that means I have a total of 3 electron domains. And 3 electron domains, no lone pairs? Well, that is trigonal planar. Okay? And because there's no lone pairs, this name is going to be the same as the molecular domain name, as long as there's no lone pairs, okay? And that's why you see the trigonal planar look like this. I could actually, I'd have to take this hydrogen off, but I'll show you what that looks like. You take that carbon and you just grab another bond. See, this is the fun part, whoops, which you guys don't get to do. This cool fun part is you get to break and make these two things. Okay, looks just like that. There is your carbonate. Sorry, I didn't put the red ones down here, but there is your double bond. And then you just take this double bond off and move it around somewhere else. But it's still trigonal. There is your 3. If you look at it like this, it looks like you have like 4 regions, but you really don't, because remember the doubles count as 1 region. So if you look at it like this, there is your 3 trigonal planar. Okay? So really have fun with that simulation, because honestly, I would be using that simulation to help with homework questions too. Right here, I lectured on it. I went nice and slow. The difference when you have those 4 electron domains. And the difference between 4 bonds, 3 bonds plus a non-bond, and 2 bonds plus 2 non-bonds. Regardless, there's still 4 regions, but the shape changes and the angle changes. So I want you to go through this, ladies and gentlemen, and read it so you can actually see what we just did. I'm just not going to repeat the same thing again. So some key things also in here, there's bolded regions. Bond angles decrease as the number of non-bonding increase. And that should make sense to you right there, because that's what the picture is showing you. Bond angles decrease from here to here to here because your lone pairs are increasing. So when you have more non-bonding, less non-bonding, your angles will start to decrease. Non-bonding pairs experience less nuclear attraction. Very key. Remember, nuclear attraction is attraction to the nucleus, because lone pairs have a greater electron-electron repulsion. So they are making that attraction to the nucleus more and more weak because they're trying to get away from those electrons. So they tend to space out more. They tend to spread, and that's what changes angles. Okay. Non-bonding pairs therefore take up more space than bonding pairs. I think we've covered that also. So like I said, please go through here and write some notes. There's some very important stuff that we just talked about in here. Okay, I'm just not going to build them again since we just did that. Now expanded octet. Okay, and let me get my setup going. So I'm going to use Mr. Purple, and we're going to start with when they have 5 or more bonds, or 5 or more regions. Okay, so expanded valence, and we look at a couple of them. So basically atoms past period 3 can do that expanded octet. So remember when we saw in chapter 7 that little picture of the periodic table? So anywhere between phosphorus, sulfur, chlorine. I'm trying to think who's under phosphorus. I think that's arsenic, selenium, and bromide. And I completely apologize if I do not have those elements in the right spot. But any of those, they can possibly do more than 4. They can possibly. It's because of those d orbitals. They can actually put more than 4 because remember the d orbitals have 5 possible orbitals. So this is when you have 5 to 6 electron domains. And we do not, ladies and gentlemen, in AP look past 6. And you're probably like, thank goodness, because I'm already like stressed out as it is. So if it has 5 domains, we change the name. Instead of trigonal pyramidal, we call it bipyramidal. Because that word bi in chemistry sometimes means 2. We're so used to the word di in chemistry means 2. But pyramidal, oops, probably helps to spell the letters in the correct location. Pyramidal means 3. So if you add that up, 2 and 3, bipyramidal, that means 5 regions. Octahedral, and I'll show you why it's called octahedral, because it usually never makes sense to student. Octa means 8. So why does it mean it has 6 regions? Well, I will show you the picture of why. Octahedral has 6 electron domains. So the most stable configuration, so if I get my Mr., we'll just call this Mr. Phosphorus, okay? And hopefully I pick the right color one, because we don't usually have a lot of molecules to practice with when it comes to expanded octet. So if you see right here, there it is, okay? So if you see, oops, I keep going outside of my pictures, dropping atoms too. So if you see right here, if I kind of put it, if I tilt it around, what do you notice? Well, you have right here, from this top down to the bottom, look at that bond angle going on right there, the top to the bottom, okay? But then also look at right here, from here to here. And if I twist it, from here to here. And if I twist it, here to here. You actually have 2 sets of angles going on. So from right here to right here, you actually have 90-degree angles. As soon as all I have to do is just rotate this like on a y-axis, but then stare at it this way. Kind of trippy. Oops, I'm trying to line it up. There you go. What do you notice right there? Angle from here to here, 1, 2, and then 3. Doesn't it kind of also look like trigonal planar? You have 2 angles. You have 90-degree angles here to here from top to the sides, but then when you rotate it like this, you have 120s, okay? So think of it kind of like a carousel. So from here to here, dang highlighter. From here to here, you have your 90-degree angles going from all over the place, but then in this kind of circular pattern, like right here, these 3 bonds, this one, and this one, you have 120s. So when you're labeling these bond angles, that's what it looks like. So if I still have that simulation open, yes, I do. So let me pick one. Should be, yep, this one. There it is, okay? So you have bond angles. If I kind of rotate it a little bit like this, trying to bring it, there you go. So best I can. So right there, there's your 90 degrees, but I don't think it's going to show you the other bond angle. And then, oops, about right there. And then you see right there, from this green one going all the way to this green one, from here to here. And it's trying to do it, but it's just not going to put the words, oh, there it is, right there, 120. Okay, so let me rotate it a little bit that way. There you go, 120. But then you also have the 90 degrees too. So the 90 degrees, oops, trying to make it bend down some more. It doesn't want to bend. So there's your 90. And then if you rotate this, kind of look this way, there we go. That's a beautiful picture. 120, 120, and 120. Okay? So I'm telling you, the simulation is really going to help you with the drawings. You have what's called axial positions and equatorial positions, and basically they just mean, are they pointing up or to the sides? And as you see, your axials, you have 2 of them right here, your axial on top, and then these right here, these 3 kind of like carousel little things right there, those are your equatorial. And I want you to keep reading through here, okay, because I'm going to show you how to draw these pictures. And then if we have an octahedral. So as I am building it, I'm going to take some of my bonds away. Usually with this yellow one, because it actually has the 6 holes in it, and for time purposes, I'm not going to put the little bonds on them. There you go. There we go, and there we go. All right. So why is this bad boy octahedral when it only has 6 regions? So if you look at it like this, I have the region, and I'll kind of hold it down here. I have the region on top and the region on the bottom. So there's two regions. But then when I tilt it this way, I have these four going around it. Okay. So where's the octa? Well, here it is. Ready? It's between them. From here to this one, there's one bond angle. And two, if I twist it, there's two. Twist it again, 3 and 4. There may be 6 regions around the central atoms, but you technically from one atom to the other, you have a bond angle of 90 degrees. But you have it 1, 2, 3, 4. You have it 4 times. And what? Look at if I do this, flip it. You have another 4. There's 1, 2, 3, 4. And the last I checked, 4 on top, 4 on the bottom. There's your octahedral, okay? Because it has to do with the bond angles. So from here to here, there's my 90 degrees. And from there to there, and there to here, and there to here, they're all 90 degrees. So in square trigonal bipyramidal, you have 2 different degrees. And you have to list both of them. But in octahedral, you have 8 possible 90-degree angles. Okay, so as you read through here, it's called those faces and vertices that you probably learned back in middle school, vertex and vertices and faces and corners and stuff like that. There are truly 8 of them. So we're going to go through the shape names. I'm going to have you go through the notes, read through it, but I want you to actually physically see what it looks like. So here is our last table. All right, let's concentrate on Mr. Square Pyramidal. If it has 5 bonds, no lone pairs, you're still going to have the same 2 bond angles. Okay, so we still have these same 2 names. They are the same. PCl5, definite one that does this. But what if now we start adding a lone pair? So now I'm just going to take one off. And, you know, I'll do exactly what the picture does. I'll take one of these sides off. Okay, so there you go. I have one of these sides. So let me show you why the name is called seesaw. Think of back in the day when you were on the playground playing and these things called teeter-totters. Let me rotate it this way and check it out. Doot, doot. You sat on one side, your homie sat on the other side, and you guys went back and forth. It's called a seesaw, aka like a teeter-totter. But you kind of look at it this way with the lone pairs sitting on the top. That's its name, called seesaw. Sulfur, and I think you guys even asked me about this video, this problem in AP Daily, where you had the sulfur lone pairs on top, and then you got the fluorines that kind of like branched out, just like that. Okay, there's seesaw. What if I take another bond off and put a lone pair? So 3 plus 2 still equals the 5. And now you get a name. There's seesaw. And now you got a name what's called T-shape. Okay. So what I'm going to do is I'm going to take another bond off. And it doesn't matter which one I take off. Take a bond off. And now lone pair there. Lone pair right there. So 2 lone pairs. And look what you got. T-shape. Literally that's the name. T-shape. Okay. So when you draw it like a Lewis structure, it looks like this. The lone pairs kind of gang up in the corner, and you got the fluorines on the side. And I'm not going to draw the lone pairs for time purposes, but you got those lone pairs in the corner, as you see right there, in the corners. And then there's your fluorine. There's your T-shape. And if we still want to take another bond off, and now you have more lone pairs than bonds. And that can happen. So take another one off. Oops, let me go right there. I meant to take the other one off. There we go. And look right there. Lone pair, lone pair, lone pair. What's it going to look like? There's Mr. Linear. You've seen the name linear before. Linear with no lone pairs. Now linear in 3 locations. And usually the noble gas tend to do this. So you'd have xenon, and we usually, when we're drawing it on paper, we would draw it like that. And the two fluorines coming out to the sides. Okay? And that is the difference of them. Here's the cool part. All of these angles are all the same. Thank goodness we don't have to keep learning different angles. But that is all the angle changes, because regardless with the lone pairs, they're not going to change the angles that much. And if you do that on the simulator, so let me go back to model. Let's put 5 bonds on here. So there you go. Is that 5 bonds? Yeah, 1, 2, 3, 4, 5. Let me make it look this way. And let's say I take one of these off and add a lone pair. Okay, look at it, still 90 and 120. Even if I rotate it, let me try to get a better angle. And that's the hard part, trying to get the best angle of this. Okay, still 90 degrees. If I take a bond off, slap on another lone pair. Okay, so there's your T shape. Notice the angle. They're still 90 degrees. They're just not showing the 120 part. And let's say I take another bond off. Slap on a lone pair. Ta-da! Look at that bond angle, 180. 180, there's your linear. So I need to correct that because I meant to say linear was 180. Oops, let's make that line not go all the way to the bottom. Oops, right there. So with this one, you're going to get a bond angle of 180. Okay? The last one's octahedral. Okay, so let me bring back Mr. Sulfur. Okay, usually sulfur, who's under sulfur? Selenium, anybody group 6 can do this. So we already looked at why it's octahedral. Every time you go through each one of these 4 quadrants, so think of it like the quadrants, you got 4 on top and 4 on the bottom. So that's why it's called 8. However, there are 6 regions, no lone pairs, called octahedral. So this is when you're going to get sulfur. So if you actually did the dots, you'd have a bond coming out, and then each one of these, they kind of split. Well, if you draw that like this, it doesn't really truly represent what you're actually staring at. So that's why on paper, it's very deceiving on the shapes. If we add a lone pair, and now basically just taking one off, okay, so there you go. Lone pair on top. We have a new name for it. If you look at it like this, doesn't it look like it makes a square? Okay, looks like it makes a square to me. So we call it square. So there's your square going up, down, to the bottom. We call it square pyramidal. And we call it pyramidal because of that one set of lone pairs. So square pyramidal, because right there, there's your square. And, cool part, all of these angles are still 90, no matter what. But now if we add another lone pair, so take this guy off, and there it is. There's your square. Even if I flip it, I still got a lone pair on each side, but planar means flat, okay? Pyramidal is not flat, okay? And I'm going to put right there, pyramidal, not flat. So even when we did it for trigonal pyramidal, same thing, not flat. So we're going to actually go up and make that note too. Pyramidal means it's not flat. And you can see the difference between it. If I get my Mr. Ammonia back, you'll see the difference of what we mean by planar and flat. So if I put it, sorry, trying to get my camera to agree with me. If I notice the difference, I can keep pushing on this and it won't go flat unless I actually hold on to it, okay? But this one right here, flat, done, okay? So I'm sure you can see the difference between it. A lot of names and a lot of angles, ladies and gentlemen, and the only way that you're going to learn it is by practicing, okay? So this is what I want you to do. I want you to take the remaining of these examples right here, and all of these are expanded octet. I want you to draw them, but tell me the names. So you're going to make a list, electron domain name, and tell me the name. And then molecular geometry name, and that's fine. If you want to abbreviate like that, tell me the two names. Okay, so we just drew sulfur tetrafluoride right above. So these four, which means don't do NAS, go old school with the dots. I want to see the names and the pictures for all of them. Okay. To end up these notes, ladies and gentlemen, you can actually have molecules that are really big that have different centers. So shapes of larger molecules, and this will end it up, although the molecules and ions we are considered usually contain only one central atom, the problem is what happens if you have more than one central atom. So this right here, this is called Mr. Acetic acid, aka vinegar. And what you'll notice is it has a center atom right there, and a center atom right there, and a center right there. Okay, so every one of those are central atoms. And how do you know that they're central? Is because these guys on the outside, these hydrogens, they're not connected to anybody else. So they're what called terminal. Terminal means outside. Oxygens only connected to carbon. This hydrogen only connected to oxygen. So what you would have to do is figure out every central atom's angle and shape. So right here, let's start with this first carbon. I see 4 bonding regions, and only this carbon has no lone pairs. So 4 bonding, no lone pairs. Well, that looks like Mr. Tetrahedral. And right here, carbon, I see 1, 2, 3, 3 bonding regions, no non-bonding, and that still equals 3, and that's called trigonal planar. If the word trigonal pyramidal was coming up in your head, only pyramidal if there would have been lone pairs sitting on that carbon. Then it would be pyramidal. But it's not pyramidal because there's no lone pairs on that carbon. Okay? And what about this oxygen? I know you're staring at it saying, ooh, that looks like linear. I think it's linear. Well, don't be betting on linear because you have 2 bonding, 2 non-bonding, and that still has to equal 4. So electron domain name is tetrahedral, but it's right there, tetrahedral, but its molecular geometry name, because it has lone pairs, the molecular geometry name would be called bent. Okay, so right here, I put the picture of this one in the book because I wanted you to see a molecule in your notes of when you actually have more than one central atom. Okay, so right here, tetrahedral, trigonal planar, and tetrahedral, but remember, molecular geometry name is called bent. And I even put the angles on here too. So tetrahedral, we would even accept the angle 109. 109.5 is the true angle. Trigonal planar, remember, take 360, divide by 3. And right here, this is for tetrahedral. However, when you do the shapes, when they have lone pairs, you do not do the electron domain name. You do the true shape name, which that means his bond angle would be 105. Okay, so that is how you figure it out if it has more than one central atom. I'm going to let you read through here so that way you can also see what I did. Okay, but I'm showing you the show. Let's practice a couple. Predict the approximate values between the H, O, and C and the OCC. Okay, so I'm going to highlight what they're asking you to do. So right here, they want the bond angle between those right there. So let's do that one first. And I like to sometimes draw it its true shape. So if this guy right there is the central atom because they want between the H, the O, and the C, that oxygen's ganging up on those bonds. So it really looks like this. So I have 2 bonding regions, 2 non-bonding regions, and that equals 4 total regions. So who has 4 total regions? Well, that's tetrahedral. Okay. However, that's the electron domain name. The molecular domain name would be called bent. Okay, so they want you to figure out what would be the bond angles. Well, I'm not basing my bond angle off tetrahedral. I'm basing my bond angle off of the true name called bent. And the bond angle would be 105. If you want to put 104.5, that's also fine too. Okay, but now what about the other one? The OCC bond. So I'm going to do that in a different color. They want this between the C, C, and that O right there. So in this case, that carbon right there, he is now the central atom. So I'm going to draw it over here. So they want this, this, and this. I don't care about the rest of the stuff around it because I'm only focused on this guy right there. So what do I see? I see 1, 2, 3, 3 bonding regions, no non-bonding regions. I don't see any lone pairs on that carbon. So that means he has 3 total regions. So what would be his electron domain name? The electron domain name for 3 no lone pairs, well, that's trigonal planar. And because there's no lone pairs, it's going to be the exact same name for the molecular name. That makes it easy. So that means I'm basing it off a trigonal planar, which means his bond angle would be 120. Okay, so I think you're getting the hang of this. You just need to practice, but it is a lot of information in one section. Let's try another one right here. Predict the HCH. And it doesn't matter which one right here that you pick, this one or that one or this one. So I'm just going to pick the one that's right here from here down to there. And I could have picked the one that was on top. So we'll do that one in one color. So let me put it over here. So H, C, and then you have these over there. So they want you to look at that. I have 4 bonding regions, only focusing on that carbon. 4 bonding, oops, sorry, trying to, and 0 non-bonding regions. Well, if you haven't figured out by now, 4 bonding, no non-bonding, that's tetrahedral. And tetrahedral has a 109 degree. Well, now they want the CCC. So in a different color, they want this one right there from the CCC. You're not going to see them draw triple bonds or double bonds in the one that they want. Okay, so don't get too confused. They want the angle between the C, C, and C. So right there, they want you to focus on that central atom. So I don't really care what else is surrounding it. I just need to focus on him. I see 2 bonding regions, and I know you're saying, wait a minute, there's 4. No, there's not. There's 4 bonds, but regions, 2 bonding regions, no non-bonding regions. Who has 2 and no lone pairs? That's linear. Okay, that's linear because there's no lone pairs, and linear is 180. And you're probably asking, well, linear for who? Electron domain or molecular geometry? And it's the same name for both domain names. Okay, so you just need the hang of it. You just need to practice. If you want, and yay, we're done. Then we're going to throw polarity into this craziness. If you want to practice that simulation, ladies and gentlemen, just go to the notes, type in that